Good afternoon. You are welcome to the second week of the facilitation on PHY407, which is solid state physics 2. Well, we started this class last week, and I think you all have the course outline or the facilitations plan for the next 8 weeks. So last week, we started by giving a kind of an introduction to what we're expected to learn in this course and how things are going to be done as regards to this course. So this week we shall proceed to the next thing on our capacitation plan, which is dielectric properties of solids. I think last week I started by introducing some of the concepts of dielectric properties of solid. So I will continue from where I stopped last week and try to reiterate what we discussed in details last week. So for those of you that could not join us last week, I've uploaded the video of the course that we had last week on the course page. Please try as much as possible to access the course page so that you can follow the trend of what we are discussing in this course. That would be a very good opportunity for you to be able to catch up on what we have discussed so far. So now, so this week, we continue from where we stopped, as I said. So our discussion this week uh, will be centered on, we have discussed extensively about dielectric properties, which is up to page 11 on the course material that I sent to you 2 weeks ago. So I now continue from local electric field. So what is local electric field? In local electric field, what is of importance to us is that every material is made up of a very large number of atoms and molecules. You cannot talk about a materials without trying to understand the constituent atoms or the molecule that constitute the materials. And also an atom consists of a positively charged nucleus and also a negatively charged electrons. These are the major properties that contribute to the properties of an atom. Also, a system consists of two equal and opposite charges, Q, separated by a certain distance. D is an electric dipole. That is, you can have what is called an electric dipole when you have a system of two equal and opposite charges. That is, you have a charge Q of the same magnitude, but they have different signs, that is, different polarity. So, and they are being separated by a distance Q. So, if this happens, you have what is called an electric dipole. So, when atom, a molecule of a dielectric is placed in an electric field, that is, when you put an atom or a molecule of a dielectric materials in an electric field, what happens? The positive and negative charges feel the opposite forces and are separated, forming a dipole. So now let's look at a very good example. Suppose the charges minus q and plus q are placed respectively at distance d over 2 and negative d over 2, as we have in this diagram. You have this, this is the first charge, negative charge, and this is the positive one. So there is distance of separation between them. So we say that where R1, R2 are the distance of x, that is the magnitude of the potential due to the system at the point x. So if you have this point x now, so the distance from negative q to x is R2, because this is the second charge. Then this is the first charge. From here to this place is this. So now from the center now to x is r, which is more or less like uh the resultant distance. So if theta is the angle between the axis of the charges and the opposite vector of x, then we can write the distance 1 over r1 to be approximately 1 over r plus this cos theta over 2r squared. The same thing for r2, which is negative now. So if you substitute this and this in this equation, this potential equation, this potential expression, q over 4 pi epsilon naught into 1 over r1 minus 1 over r2, and we perform analysis on them, numeric algebra analysis on them, we can establish that this potential is equals to this. So the dipole moment P is the vector along the axis of the dipole pointing in the direction negative Q to positive Q and having a magnitude PD. So in terms of dipole moment, you can see that equation 1.12 becomes, so if you try to look at this equation now in terms of dipole, QG now can now be P. So that's why you have this. So which is now equals to P prime dot R. Dot R now is cos theta. So you can now see that using the grad of 1 over R, you now have negative this over this. So equation 1.13 can be written in this form now. Theta, the potential to equals to this, which is this. So where phi naught is the potential of a unit charge, that is, the phi naught here is the potential for a unit charge when you are considering just a unit charge. So the field of an electric dipole may also be expressed in the following way. You can express the field in this way. The field now is the grad of the potential. So, and we know what our potential is. By the time you put it there, you apply the grad to work on it, then you have this expression. So in the CGS system unit, equation 1.15a can be written in this format. So now, considering a cubic crystal dielectric, which is shown in figure 1.2, and assume an electric field of magnitude E naught is applied parallel to one of the axes of the crystal. The field will push the positive charge nucleus of the atom of dielectric slightly in direction of the field, because the field will try to attract it, and the negative charge electron in the opposite direction, as shown in figure 1.2. We say that the atom is polarized under the influence of an applied electric field, and the charges are called polarization charges. So if there is an applied electric field, polarization will take place and charges will be polarized. So the negative will move away while the positive will also move into another direction. So this is what we are trying to say. If you look at this picture now, we have negative and positive charges in the system like this, in a dielectric material, going in negative in opposite direction to each other when you put an electric field. So you see that all the positive moves to one direction and all the negative move to one direction. If this happens in the presence of applied electric field, we have a polarized spherical dielectric. If you now consider them in a rod, so the dielectric is equals to 0 in this case also, then you can see that it goes in one single direction. So the polarization P is defined as the dipole moment per unit volume averaged over the volume of a cell. The total dipole moment is defined by this. P is equals to this Qn, that is the total number of charges, then times r, the distance. So let us imagine that a small sphere is cut out of the specimen around the reference point. Then E1 is field of the polarization charges on the inside of the cavity left by the sphere, and E2 is the field of the atom within the cavity. So E1 will be outside on the cavity, and E2 will be within the cavity. So the polarization charges on the outer surfaces of the specimen produce the polarization field E3. So the depolarization field is opposite to P, that is the field E naught. E3 is called depolarization field because within the body it tends to oppose the applied field E naught, as shown in figure 1.2 that I showed to you the other time. So now we can also look at the local electric field at the local electric field at any atom of the dielectric may be written as this. So it is just the summation of all the field involved in the system. So the contribution E1 plus E2 plus E3 is the total effect at one atom of dipole moment of all the other atoms in the system. So which is equal to this. This is now equal to what we derive when we have charges in opposite charges separated by a distance and you have a polarization that takes place. So this can be written in this format. which is equation 1.18. So the polarization field is opposite to P. So Lorentz shows that the field E1, due to the polarization charges on the surface, form a continuous distribution. So the density of the surface charge is equals to P cos theta, where theta is the polar angle along the direction of polarization in figure 3. So this is what we are trying to say. So E1 will now be integral from 0 to pi of R, capital R minus 2 pi R. So this is how to compute polarization in a sphere. So that the field E2 due to dipole within the spherical cavity is the only term that depends on the crystal structure. It can be shown that for a reference site within the cubic surrounding a sphere, that E2 is equal to 0 if all the atoms will be replaced by point dipole parallel to each other. So for specimen in the charge for specimen in the shape of ellipsoid oriented with one of the principal axes parallel to applied field, it can be shown that the depolarization field will be parallel to applied field, and E is equals to minus mp epsilon naught. So the constant n is known as depolarization factor. So if ps, py, bz are the component of polarization along the x, y, and z, so p refer to the principal axis of that ellipsoid, then the component of the polarization field are written as, so this is E3 along x, along y, and along z. So now, for you to test your knowledge or to test your understanding of what we have discussed today and also last week, so you can try to go through to try to explain what polarization is and what depolarization fields are. So also, you can also try to look through the notes and define what are dielectrics and also what is meant by dipole moment. So these are major things that you are expected to have understand or pick the definition in what we have discussed so far since last week up to this week. So by next week, we shall be looking at dielectric constant and polarizability. But I will give you a kind of an hint into it before next week. So if you look at, say, let's consider the dielectric behavior of molecule, which have a permanent dipole moment. So the dielectric constant epsilon has been defined for an isotropic or cubic medium relation relative to vacuum as this. Epsilon is equals to d over e. D in this case is displacement, plus 1 plus p over epsilon e. You know what p is. P is polarization and E is electric field, which is equal to 1 plus psi. This psi is called electric susceptibility. So the susceptibility is related to the dielectric constant by this definition. So also, if the field is not too large, the strength of the induced dipole moment in an atom I is proportional to the local electric field acting on the dielectric. That is, you have Pi proportional to this and Pi is equals to this. So where epsilon I, no, where alpha I is the polarizability and Pi is the dipole moment of atom I. So polarizability has the SI unit of this, but is more often expressed as polarizability volume with unit of centimeter cube or Armstrong cube, which is equal to 10 to the power of minus 24 centimeter cubic. So the polarization of a crystal may be expressed approximately as the product of polarizability of the atom times the local electric field, so which is equal to this, where Ni is the number per unit volume of atom I. So the electric susceptibility can now be defined as this. So P all over E, we know what P is, we not know what E also is, so you have this. So if you use this equation now and the Lorentz relation, you will have this. So take note of this because you can be asked to write this in terms of Lorentz relation in an examination. So this will lead us to equation 1.25, and this equation 1.25 is what we call the Clausius-Mostick equation that expresses the relation between the dielectric constant and the atomic polarizability. So we are going to stop here today. So if you have any questions, you are free to ask me. If you have any question, you are free to ask me. So in the absence of no questions, so I think we are going to stop the class for today. So hopefully we meet next week. So also try as much as possible to check the course page to have access to the recorded versions of the class. That will be of help to you when you are doing revisions and trying to go through what we have discussed so far. So thank you for coming. See you next week.